When you double-click an application, or run a command in the terminal, or start a web server, where does execution actually begin? Every program, no matter how complex, has a single defined starting point. Before the CPU executes its first instruction, before memory is fully initialized, before threads are spawned, something determines one key thing: start here. That starting location is called a program entry point. And today, we're going to break down exactly what program entry points are, how software execution begins, what happens between clicking run and the first instruction, how entry points differ across programming languages and operating systems, and why misunderstanding this topic creates confusion in system design and architecture. Let's start with the simplest definition. In computer science, a program entry point is the first instruction executed when a program starts running. That's the key phrase, the first instruction. Because no matter how large a program becomes, even millions of lines of code, execution must begin somewhere. And the entry point is the boundary between the operating system, the runtime, the CPU, and your code. Most developers first encounter entry points through a main function. For example, in C or C++, you often write main. In Java, you write a static main method. In C#, you write main. In Go, you write main. And in Python, you might not write a main function at all because top-level code runs immediately. But here's an important thing to understand early. The entry point is not really a function. At the lowest level, the entry point is an address. It's a memory address where the CPU begins executing instructions. The CPU does not understand functions, it does not understand classes, it does not understand objects, it understands addresses and instructions. So when a program starts, the CPU's instruction pointer is set to a specific address, and the CPU begins executing machine instructions from that location. Everything else, functions, classes, modules, threads, servers, emerges from that first instruction. So what actually happens when you run a program? Let's slow it down. When you start a program, the operating system creates something called a process. A process is basically a running instance of your program, with its own memory, its own resources, and its own execution context. Once the process is created, the operating system allocates memory for it. Then it loads the executable file into that memory. Then it sets up the process environment, things like command line arguments and environment variables. Then it creates the first thread. And finally, it sets the CPU's instruction pointer to the entry point. At that moment, execution begins. The CPU loads the instruction located at that entry address and executes it. Then it moves to the next instruction and the next and the next. This is what software execution really is. It is simply a sequence of CPU instructions executed in order, starting from a defined entry point. Now here's where it gets interesting. In many compiled languages like C and C++, the main function you write is not the true entry point. It's the entry point from the perspective of your code, but not from the perspective of the operating system. At the OS level, the real entry point is typically a function called _start, written like _start. That _start symbol is provided by the runtime startup code, not by you. Here's the idea. When the operating system starts your program, it doesn't call main directly. Instead, it jumps to _start. And _start does a bunch of setup work before your main function is ever called. For example, _start sets up the stack. It prepares arguments. It prepares environment variables. It initializes runtime state. And only after all of that does it call main. Then when main returns, _start handles cleanup and tells the operating system that the program has finished. So if you want the most accurate mental model, it looks like this. First, the OS jumps to _start. Then _start prepares the runtime environment. Then _start calls your main function. Then your main function runs. Then when main returns, _start performs shutdown logic and exits the process. So technically, the first instruction of your program is not inside main. It is inside the runtime startup code. This is a huge detail that many developers never learn, because most of the time you don't need to think about it. But the moment you start caring about low-level execution, debugging startup crashes, or understanding what a runtime does, This becomes extremely important. Now let's compare this to managed languages. Languages like Java and C# have an even more layered execution model. In Java, your program does not run directly on the operating system. Instead, the operating system starts the Java virtual machine, which is itself a program. So the OS creates a process for the JVM. The JVM has its own entry point. The JVM initializes itself, it loads your class files, it performs bytecode verification, it sets up memory management, it starts the garbage collector, and then it searches for a specific method signature. In Java, that signature is public static void main with a string array as input. Once the JVM finds that method, it calls it, and that method becomes the entry point of your application inside the runtime. So the execution hierarchy looks like this. The operating system starts the JVM. The JVM starts itself. The JVM finds your main method, then your main method runs. So your program's entry point exists inside another program's execution. This is also true in C#. In C#, the operating system starts the .NET runtime. The runtime loads assemblies, initializes the managed environment, and then calls your main method. And in languages like Python, something similar happens. The operating system starts the Python interpreter. The interpreter loads your script, and then executes top-level statements line by line. So in these languages, you're not writing the true system entry point. You're writing the entry point for your code inside the language runtime. Now let's connect entry points to threads. Every process begins with at least one thread. This is not optional. The operating system creates the first thread, often called the main thread, and the entry point defines what the main thread starts executing. So the entry point is essentially the starting function of the main thread. Execution begins in one place, in one thread, and from there, the program may create more threads. But every thread in your program originates from that initial execution context. Even if your program eventually has hundreds of threads, all of them exist because the first thread started running at the entry point. So the entry point is not just a technical detail. It's the root of your program's control flow. Now, entry points become even more interesting when you look at different kinds of software, because not all programs behave the same way. A command line program usually starts, runs some logic, and exits. So the entry point leads into a relatively short and linear control flow, but a server is different. A web server still has an entry point, but instead of finishing quickly, the entry point starts the server loop. It initializes configuration, loads dependencies, opens network sockets, and then begins listening for connections. From that point on, the program is often running indefinitely, so the entry point becomes a long-running orchestrator. It sets the system in motion, and then the system continues operating. GUI applications are another special case. A desktop application still has an entry point, but after startup, it typically enters an event loop. The program stops being linear. Instead, execution is driven by events. Mouse clicks, keyboard input, window events, timers. The entry point starts the event system, and then the event system controls the flow of execution. Embedded systems are different again. In many embedded environments, there is no operating system. When the device powers on, the CPU begins executing firmware immediately after reset. In that case, the entry point is literally the first instruction after power on. The entry point is defined by hardware and memory mapping, and there is no OS process creation step at all. It's just CPU, memory, and instructions. Now here's another major concept. Many developers confuse entry points with application logic, or they confuse entry points with framework lifecycle. These are not the same thing. Your entry point is the start of execution. But in modern software, your logic might not run immediately. For example, consider a Spring Boot application. You might write a tiny main method that looks simple. But when you run it, a massive amount of work happens before your application is actually ready. The JVM starts. Then the Spring framework initializes, then configuration is loaded, then dependency injection occurs, then beans are created, then class path scanning happens, then proxies are built, then the web server is started, and only then does your application become operational. So the entry point is the beginning of a chain reaction. It's the first domino. And if you want to understand startup performance issues, initialization failures, dependency loading order, and boot time bugs. You need to understand what happens immediately after the entry point. Now let's zoom all the way down to the CPU level. At the lowest level, the CPU has something called a program counter, also called an instruction pointer. This is a register that stores the address of the next instruction to execute. When the operating system starts a process, it loads the executable into memory, and it sets the instruction pointer to the entry address defined in the executable metadata. For example, on Linux, an executable file format called ELF contains an entry point address in its header. That header literally says, "This is where execution begins." The OS reads that value and sets the instruction pointer accordingly. From that moment onward, the CPU simply executes instructions. Instruction after instruction after instruction. The CPU does not know whether the program is written in C, Java, Python, Go, or anything else. At the lowest level, it's all just machine code. So a program entry point, in its purest form, is simply the first address the CPU jumps to when the process starts. Now let's bring this back to architecture. Why do entry points matter? Because they define the route of control flow. They define the startup sequence. They define dependency initialization order. They define how and when threads begin. They define how the runtime and the application connect. And they determine what starting the program really means. If you don't understand your entry point, you don't fully understand your system's execution model. And that matters in real engineering. It matters when your system takes too long to start. It matters when startup crashes happen. It matters when configuration loads in the wrong order. It matters when thread bugs occur early in runtime initialization. It matters when you debug deadlocks during boot. And it matters when you design large systems where startup and runtime behavior must be predictable. Now let's clear up a few common misconceptions. First misconception: main is always the first thing that runs. Not true. Runtime bootstrapping runs before main in most languages. Second misconception: entry points are just required syntax. Not true. Entry points define execution control. They are the root of the entire program's behavior. Third misconception: a program can have multiple entry points. At runtime, execution always begins at one address. You can have multiple ways to start a program, like different commands or different scripts, but the CPU begins executing at one entry point. Fourth misconception: threads start independently. Not true. Threads are created by code running in the first thread. All concurrency in your program originates from the initial execution context. So let's summarize everything. A program entry point is the first instruction executed when a program begins. It is the root of control flow. It is the starting point of the main thread. It is the boundary between the operating system and the software. And it is the beginning of runtime initialization. From a single deterministic point, processes begin, threads spawn, servers run, applications respond, and systems scale. All software execution, no matter how complex, starts from one defined entry point. And once you truly understand that, you understand software execution at a much deeper level.